We are continuing the discussion on deformation of bodies in this video under deformation of bodies under applied forces. Now, in addition to the deformation in the direction of applied force, there are other remarkable properties that can be observed while a body is being deformed. For example, if you consider let's say if you consider a body like this and assume that this is being subjected to a tensile force. Now, as you can see, this will be elongated, or this body will be deformed in the direction of this force. This is note that this is a uniaxial force. This is acting on one axis only. However, for a solid material, for all solid materials, the volume cannot be changed. So if there is an extension of the length, say the body changes its length from L plus delta L, the volume should remain constant. You know that because it's a solid material, so the volume cannot be changed unless there is another chemical reactions going on. If it is just a uniaxial force, then the volume should remain constant. So if the length is increased, there should be a decrease in either the depth or the thickness of the body. So we can see at the same time of a uniaxial strain, there is another strain on a different plane, and that's what we are discussing here. And as you can see, if the length is increased by this much, then to compensate for that increase in length, or to compensate for the increase in volume due to the length increase, the width should be reduced. So the final shape of the body will be this one. So this will be the final shape of that solid material or that solid body. Initial was this, and because the length extended, there is a strain or a deformation on another axis to compensate for the increase in increase in dimension in one axis, along one axis. So these deformations are greatly exaggerated just for the illustration purpose. The physical fact may be restated. If a solid body is subjected to an axial tension, it contracts laterally. So an axial tension along this axis, and there will be a contraction along the other axis. So that is the essence of this concept. Now, what if there is an axial contraction or an axial compression? So let's see what happens if it's a compressive force. Say for example, you have a force acting like this, then applying the same concept, you can see the body will change like this. Again, the change in dimensions are greatly exaggerated just for the purpose of explanation. So you have had a contraction in length on either side, and to compensate that contraction, you had an expansion in or expansion on the other axis. So an axial deformation always creates a lateral deformation of the opposite sense. So you can see here it's a plus delta L, and therefore it is minus delta T, assuming this as thickness of the body. Whereas here it's minus delta L and plus delta T. What I'm trying to say is the axial and lateral deformations will always be of the opposite magnitude. Now, what is Poisson's ratio, or what is the property that we are discussing here? All this concept, I discussed all this concept just to explain one remarkable property of all solid materials, which is called Poisson's ratio. So that is Poisson's ratio. Again, the Poisson's ratio is using the same concepts as strain. Poisson's ratio usually is denoted by nu, which is pronounced nu, and that is equal to lateral strain over axial strain. And you know, these both these terms are always negative or opposite in direction, and therefore Poisson's ratio will always be a negative quantity, because if axial strain is positive, lateral strain will be negative, and vice versa. The value of nu fluctuates for different materials over a relatively narrow range. Generally, it is in the order of say 0.25 to 0.35. This is the general value of Poisson's ratio for most materials. It is normally attained by materials during plastic flow and signifies constancy of volume. As I said before, the volume of the material should remain constant. And Poisson's ratio, in all our discussions, Poisson's ratio will be used only when material behave elastically. Again, when you have when you consider Poisson's ratio, it should be noted that Poisson's ratio, or the consideration of Poisson's ratio, does not cause any additional stress other than those considered under the usual stress calculations. So if a body, let's say for example, if a body like this is, when we consider the Poisson's ratio, if a body like this is subjected to a tensile pull force like this, then it will naturally collapse, or it will naturally change its dimensions like this, which means there is an increase in length and a compression in width or thickness of the body, unless this sides are restrained from moving. So the stress generated will be same unless there is a restriction or the prevention applied for the deformation in the lateral dimension. So for example, if a body is restricted, say if it is restrained here, if it is fixed at either ends, say this is a fixed end and this is a fixed end, and then the body is applied to force, then you can say there is an additional stress generated at either side, because the body tried to usually the body will try to go to a shape like this. However, because you have restricted the motion at these 2 points, there will be an additional stress. So unless there is a prevention, or the deformation is restrained in the lateral planes, there will be no additional stress created by this deformation of the body. The stresses will be the usual stress that are calculated using the standard stress strain equations. So once again, Poisson's ratio is the lateral strain over the axial strain, and the value usually ranges between 0.25 to 0.35. This reinstates the volume conservation or constancy of volume for a solid material. Whenever a solid material, a body created with a solid material is pulled or pushed axially, then there will be a lateral deformation, and the ratio of lateral strain over axial strain is called Poisson's ratio, and the value of that is usually ranging from 0.25 to 0.35. The strains, axial and lateral strains, will always be opposite directions. If there is an axial pull, the lateral deformation will be a compression or a reduction in dimension, and if axial dimension is decreased, then lateral dimensions will be increased to compensate for the change in volume, or to keep the total volume of the body constant. So that is Poisson's ratio. Once again, thank you for watching. Keep watching for other topics. Thank you.